right, welcome everybody. It's great to have this Hearne Eminent lecture in person. The last time we had it was February 2020 when John Dowling was still with us. And I believe at that one, or maybe a previous one, Arlo Lando was there as well and was very happy to meet my wife, had a big smile. So we remember them today. I'm personally very pleased to have our current eminent lecturer, Nilanjana Datta, here visiting us. I've been trying to get her to visit us here for quite some time, and it's really wonderful that it happened today. Nilanjana is a professor of quantum information at the University of Cambridge, and she's from the Indian state of West Bengal. And today she met her friend Tiger, Bengal Tiger, Mike Tiger, and we have a nice photo. She graduated from Jadavpur University with a Master's of Science and did her Master's with post-MSc at Saha Institute of Nuclear Physics. She got a PhD at ETH Zurich with Jörg Froelich and Rudolf Dwarf, working on quantum statistical mechanics and the quantum Hall effect. She had a number of postdoctoral positions before landing at Cambridge. After she arrived at Cambridge, she switched her topic to quantum information theory, which is a very exciting topic to work with. And has made a number of seminal research contributions. I personally learned about her work for the first time as a grad student around 2002, 2007, 2008. I was reading a lot of papers. I read her papers. They made sense to me. So that's always a nice thing. As many of you graduate students, your experience has been when you go to the literature, it just seems like a big mess to get through. And so it's nice when people write papers that make sense. And so it's really great that a few years later, I got to meet her in person and start collaborating. She has been a major contributor to topics in quantum information, such as one-shot quantum information theory. We might hear a little bit about that today. No? All right. It's a public lecture. It's meant to be accessible by everyone. She's worked on quantum entropies, quantum communication, mathematical physics, publishing in journals like Communications in Mathematical Physics, Physics Review Letters. She's worked on additivity problems in quantum information theory, quantum dynamical systems. She's the founder of a conference series which has been extremely important for the field. It's called Beyond ID. It started in Cambridge in 2013, and it gathered a lot of the important contributors to the topic, and it's continued every year since then. And many, many, many research results have come about from this conference series. Academia can be a somewhat cold environment sometimes. Maybe the graduate students even feel that today in the room if I'm wearing a suit. But Nilanjana is a very warm person, just a very nice, welcoming personality. As part of the Beyond ID conference series, she instituted a music session where the participants not only are required to present their research, but also their musical talents. And so it is required. And so that was a very interesting experience for me and brought out more of the musical aspect of my personality. I think that's all I have to say. All right, so thank you for coming here. I'm really delighted. I'm looking forward to your lecture.
Thank you very much for this very nice. My first visit here, and really like the campus and the lakes, and talking to all the students. I wish I had come for a little longer and had a little more time. Anyway, thank you for coming to the lecture. Mark had said no formulas. So there are a few formulas, but everything should be understandable to everybody. So I'm from the University of Cambridge, and the title is Entropy, Ubiquitous, Enigmatic, and Essential. So entropy is a word which may be familiar to many of you. And you might have heard this phrase, entropy is a measure of disorder. And many of you might have seen this cartoon, this famous cartoon, where a little boy, when scolded for the mess in his room, says, I blame entropy. This is often called the messy room analogy. You might have also heard the phrase, entropy of the universe can only increase. So let's start with some famous quotations on entropy. So the first one is by Rudolf Clausius, who actually coined the word entropy. And just want to see. I'll go through, read out some of these quotations, and we'll revisit the scientific ones later on in the course of the talk. So he said, the entropy of a closed system, not in equilibrium, will tend to increase over time, approaching a maximum value at equilibrium. And then way back in between 1875 and 1946, a physical chemist called Gilbert Lewis said, gain in entropy is nothing more nor less than loss of information. And the famous theoretical physicist and cosmologist from Cambridge, Stephen Hawking, said, the increase of disorder or entropy is what distinguishes the past from the future, giving a direction to time. But entropy is ubiquitous. For example, Isaac Asimov, the science fiction writer, wrote, it will all stop someday, but not for billions of years, many billions. Even the stars run down, you know. Entropy must increase. It has also been used in the context of the Olympic motto. Chris Cleave, a writer and journalist, wrote, I think there's something extremely beautiful about the Olympic ideal and its motto, swifter, higher, stronger. It celebrates everything which is the antithesis of death, dissolution, and entropy. It is also used in art. Here's a painting with the caption entropy, and has also been used in religion. Here are some words by a Nigerian pastor who said, the sinful nature of man is the same in every generation. Man naturally moves towards entropy. We are driven towards the carnal, mundane, and the mediocre. And in business management, whether you have a leadership title or not, you have the potential to either lead your organization beyond all expectations or inhibit its growth through entropy. So entropy is enigmatic. Here is John von Neumann, a famous quantum physicist, and Claude Shannon, who was the founder of information theory. So when Shannon first proposed his famous formula for information, which we will see in a couple of slides, in 1948, von Neumann told him, you should call it entropy for two reasons. We'll come to the first reason later on in the lecture, but the one highlighted there is because no one really knows what entropy really is. So in a debate, you will always have an advantage. There is also another enigma regarding entropy, and it's to do with outer space, with black holes, and it's called the black hole entropy enigma. So what is entropy? Let us try to understand what entropy means in various contexts, starting with thermodynamics and statistical physics, where it originated, then moving on to classical information theory and quantum information theory, and touching upon the black hole entropy enigma along the way. And then let's see why it is essential. So hopefully by the end of the lecture, I will convince you can see why I chose this title. Okay, a bit of history to start with. So the word was coined by Rudolf Clausius, and he was credited with making thermodynamics a science. And Albert Einstein, whom all of you know, had this to say about thermodynamics. He thought it was the only physical theory of universal content which will never be overthrown. Clausius also formulated the famous second law of thermodynamics, which in a nutshell says entropy of a closed system always increases. So what is entropy? So let us start with the familiar phrase, entropy is a measure of disorder. And let's try to understand it. So to understand this, we need to introduce the concepts of macrostates, microstates, and multiplicity. And these notions were introduced by Ludwig Boltzmann, an Austrian physicist and philosopher, and who was one of the founders of statistical mechanics. Okay, so consider a hydrogen balloon. So a macroscopic description of the balloon is given by observable quantities. For example, its pressure, its volume, its temperature, etc. And these define its macro state. But the balloon consists of trillions and trillions of hydrogen molecules. And these molecules move around, they collide with each other, they bump against the wall. And so a microscopic description of the balloon is given by the states of each individual molecule of the hydrogen balloon. So here x1, v1 is, say, the position and velocity of the first molecule, and that's of the second molecule, etc. So the microscopic description, this entire list defines the microstate of the balloon. So there are a number of different microstates corresponding to a single macrostate. So think about it, that there are many, many, many different configurations of the individual molecules, which would result in a balloon with a given pressure, volume, and temperature. So that's what I wrote in the last slide. And all these microstates are equally likely. So this number, the number of different microstates corresponding to a given macrostate, is called the multiplicity of the macrostate. And let us denote it by this Greek symbol, omega. So then the entropy of the balloon, when it is in a given macrostate, is given by the following formula. So we denote it by S, and this is the formula. It's K, which is called the Boltzmann constant after Boltzmann, which is a tiny constant. And this is the logarithm of the multiplicity. So this is, after Boltzmann, this is often referred to as the Boltzmann entropy. So some macrostates have higher multiplicities than others. So what we see is that entropy is related to multiplicity, and multiplicity, as we saw, was the number of microstates for a given macrostate. So to understand the phrase that I've written above, let's consider a simple analogy. So let's consider 3 boxes, and each hold exactly 4 balls. So then we can say the macrostates of these 4 boxes is 4R, corresponding to 4 red balls, 3 red and 1 green, and 2 red and 2 green. So then the microstates of these boxes here would be just this, because there is no other way to arrange the red balls in the box. This box, however, has 4 different macrostates, because the green ball can be in here, in the first, second, third, or 4th position. And correspondingly here, there are 6 different arrangements of 2 red and 2 green balls. So the multiplicity omega for these different macrostates are respectively 1, 4, and 6. So now let's use the formula for the entropy and see what the entropies are corresponding to these different macrostates. So we will see that it is least for this macrostate. In fact, it is 0, because logarithm of 1 is 0. It is highest for this macrostate and medium for this. So you see directly that there is a relation between the multiplicity and the entropy. So lower the multiplicity, lower the entropy, and vice versa. So now if we look back at the popular phrase, entropy is a measure of disorder, we know how to interpret disorder. Disorder has to be interpreted as multiplicity. So there is this relation between these 3 quantities. So this famous formula is actually engraved in the tombstone of Boltzmann. So what is the advantage of this logarithm here? So if you didn't have the logarithm and just had omega, you had this very fast growing function. The logarithm is a much slower growing function. And this omega is a huge quantity. There are many, many molecules in the balloon. And so there are many, many configurations. And so by taking the logarithm, one gets a smaller and more tractable value. So this is the phrase we started with. Entropy is a measure of disorder. And the way we understand it is that higher multiplicity implies higher disorder, which implies higher entropy. So if you look at these 2 glasses, this is one of liquid water and the other of ice chips. So naively at first glance, you might think that this is more disordered and has higher entropy. but that's not correct. This is the one with higher entropy, because in the liquid state, the molecules of water have much more freedom to move around. So there are many more possible configurations, as opposed to the frozen state where the molecules are much more restricted and therefore fewer number of configurations, and which means lower multiplicity and therefore less of disorder and lower entropy. Let's move on to the second popular phase. Entropy of the universe can only increase. So this comes from the famous second law of thermodynamics, which says entropy of a closed system always increases. We will qualify this statement as I go along. So first, let's understand what's a closed system. So this is a system, here is its boundary, and an open system is one which interacts with the surroundings, which exchanges, say, heat or matter with its surroundings. For example, you could have, say, a cup of hot water. So the heat from the cup of hot water goes into its surroundings. Even some of the water molecules escape as water vapor. In contrast, a closed system is one which does not interact with its surroundings. So for example, you can take a thermos flask. So the second law of thermodynamics pertains to the change of entropy of such a closed system under a spontaneous process. So that means a process which occurs without outside intervention. And it tells us that this change of entropy can never be negative. So entropy always increases. So let's look at an illustration of the second law of thermodynamics. So consider a container with two compartments containing two different gases. Now, let's not confuse ourselves. We are not counting the number of balls as I was doing in the previous analogy. Here we are just containing a red gas and a blue gas. So I'm not a chemist. I don't think red gases and blue gases exist, but I think nitrogen dioxide is brownish orange and iodine vapor is a vivid purple. So I couldn't get those colors, but so let's consider this as a red gas and the blue gas. And consider, and this is the two compartments are in thermal equilibrium. And now consider the divider between the two compartments to be removed. So at that instant, the red gas is on the left side and the blue gas is on the right side. But now let it evolve spontaneously without doing anything else to it. So what will you see? That the blue and red molecules will mix freely. So the system moves from an ordered macro state, ordered in the sense that the red gas is on the left and the blue gas is on the right, to a disordered macro state, which is the one on the right. So let's call this the macro state A, because you're observing the red gas here and the blue gas here. And this we call the macro state B. And then you might ask, why does this happen? Why does this transition happen? The reason is there are many more ways in which the red and blue molecules can spread themselves over the whole container instead of just remaining red on the left and blue on the right. Hence, there are many more microstates corresponding to the macro state B. Okay, and we always want to tend toward higher number of microstates, which is higher multiplicity, which means higher entropy. So if you look at the entropies of this, let's call it S of A, and let's call the entropy of this macro state S of B. So we see, because it has higher multiplicities, many more microstates, many more configurations, so the entropy of B is greater than the entropy of A. So the change in entropy, that is called the delta S, which is the difference of the two, is therefore positive, and entropy increases. And this is an illustration of the second law of thermodynamics. And note that the mixing of the two gases is an irreversible process. The gases can never unmix themselves. Okay, so this was, in a nutshell, the statement of the second law of thermodynamics. It is a fundamental law of nature. So for example, we consider the closed system of a thermos flask. So if you can take a couple of ice cubes and a small heated rod and put them in the thermos flask, what will happen? Heat will move from the hot rod to the ice cubes and melt them. And why does this happen? Because of the second law of thermodynamics. Arthur Eddington, who was a famous British astronomer, said this about the second law. He says that the law that the entropy always increases, which is the second law of thermodynamics, holds, I think, the supreme position among all the laws of nature. So now with that sentence phrase that we've understood the phrase, we can easily understand this popular phrase. Entropy of the universe can only increase. Why? Because the universe is the ultimate example of a closed system. There is nothing outside it with which it can interact. So its entropy increases in accordance with the second law of thermodynamics. Second law of thermodynamics and the arrow of time. This was a phrase coined by Arthur Eddington, the astronomer I talked about a minute back. So time, unfortunately, moves only one way. We all become older, we can never reverse time, so time is asymmetric, and the past is distinctly different from the future. When an egg breaks, it can't unbreak itself. Waves break, they don't unbreak. Gases mix, they can't unmix, and we all get older. Why? So it seems like all the fundamental laws of nature don't have any direction, but the second law of thermodynamics has a direction. So Stephen Hawking said, the increase of disorder or entropy is what distinguishes the past from the future, giving a direction to time. This is a quotation from his famous book, The Brief History of Time. So what does he mean by this? So his justification is, if we were to reverse time, then we would violate the second law of thermodynamics. So the second law of thermodynamics therefore gives an arrow of time. Okay, let's move on to information theory. Entropy in information theory. So let's start with classical information theory. So what is it? It is the mathematical theory of storage, transmission, and processing of information. And the field was maybe born in 1948, when Claude Shannon wrote a seminal paper called The Mathematical Theory of Communication. So the fundamental unit of information theory, as all of you know, is something called a bit, which takes the value 0 or 1. In fact, all of the data stored and transmitted by all the digital devices that each of us uses every day is encoded as bits, zeros and ones. So Claude Shannon, in his paper, posed two questions. So the first question was, what is the limit to which information can be reliably compressed? Sorry, I missed a question mark there. So the relevance of this question must be clear to all of you, because we all use mobile phones, we send photos, we send messages, and we know that there is a physical limit on storage space. And also, if you compress your message, compress a photo, you can transmit it faster. His second question was, what is the maximum amount of information that can be transmitted reliably per use of a communications channel? The relevance of this too must be clear to all of you, because communication channels are inherently noisy. I'm sure at some point in your life, each one of you have spoken to someone else on a crackling telephone line. So for example, here, let's call her Alice, says, I will arrive at 11. And Bob hears, I will dive at 7. So noise distorts the message. So what is information? So if you read the news, you talk to somebody, you get a text message, you get information. So what did Claude Shannon do? He related information with the notion of uncertainty. He said, gain in information can be understood as a decrease in uncertainty. And that will become clear as I go on. So if there is this duality, then a measure of information can be obtained from a measure of uncertainty. And so Shannon's measure of uncertainty of an event is what he called surprisal of the event, a name which I like very much, and I'll explain why. So to understand what is meant by surprisal, let us do the following. Let us just consider rolling two fair dice, and just note the sum of the dots on the two die. So here it will be 9. And let us say, take this value to be x. So this x is a random variable. Why? Because it takes different values with different probabilities. So suppose these are the possible values that x can take from 2 up to 12. It takes a value 2 if you roll 2 ones, and it takes a value 7 if you roll a 6 and a 1 or a 5 and a 2, etc. So there are 36 possibilities. So what are the probabilities? So if you look at the probability x being 2, it is only one possibility out of all the 36. So it has a probability 1 over 36. Whereas if you consider the probability of the sum being equal to 7, there are 6 different ways you can get it. So it's 6 over 36. So now we look at the event. The event is x taking a particular value. Say x taking a value 2, 3, etc., up to 12. So surprisal of the event that x takes a value I was defined by Shannon, denoted by gamma I, and was just minus the logarithm of pi. Note that here you have a logarithm to the base 2, and that's just because we are doing information theory, where the fundamental unit is bits, so we have 2 values, 0 and 1. So here I've just plotted this function. So the red dot here corresponds to the surprisal of x being equal to 2. It's higher up there. And the blue dot corresponds to the surprisal of x being equal to 7. And what you notice is that this is greater than this. So rarer an event, now rolling 2 ones is a much rarer event than all the other options which give a 7. And so rarer an event, the more surprised you are when it happens. So that's how you get the name surprise. So rarer an event, higher its surprisal, and higher the information gain when it occurs. So this is how you want to connect uncertainty with information, decrease in uncertainty with increase in information. So in 1938, fishermen caught a fish called the silanam. It's a prehistoric fish which was believed to be extinct 66 million years ago. So this was, of course, a very rare event, a highly unlikely event. And it led to a huge gain in information. It led to a significant change in our understanding of evolution and biology. In contrast, if a fisherman goes and catches a trout, it would hardly imply any change in any theories. So what I'm trying to get across to you is that the surprisal of event is therefore a good measure of the gain in information when the event occurs. So we were talking about surprisal, but what we are interested in is entropy. So what is entropy? Entropy, which we call Shannon entropy after Shannon, is just the average surprisal. So in the example of rolling 2 dice, when you were thinking about the sums of the dots that are shown on the top faces, the surprisal was defined like this. And the Shannon entropy, which I will denote by h of x, is just the average surprisal. So the surprisal gamma I happens with probability pi. So it's just this formula. So there is a relation between the Boltzmann entropy, which I started my lecture with, and the Shannon entropy. This is the Shannon entropy, and this is the Boltzmann entropy. How are they related? Actually, this can be written in a very similar form. See, look at this 2 quantities. Other than the constant k and the use of a different logarithm, they are identical. What is this pi now? Remember, omega was the number of microstates corresponding to a given macrostate. And I told you that all the microstates are equally likely. Therefore, the probability of, say, the ith microstate will be 1 over omega for every possible microstate. So if you just substitute this, you can get back this formula. So now we can understand this enigmatic entropy phrase that Shannon said. Von Neumann told Shannon, he said you should call it entropy for 2 reasons. And the first reason he said was that because the same quantity is used in statistical mechanics. And that's because of this similarity between the 2 relations. So there's another interesting interpretation of entropy. Let's play a simple game. So I pick the letters A to F of a Scrabble game, and then I put them in this little bag. And I ask you to pick any letter from A to H from that bag. And I have to guess the letter you have picked by asking you questions. But you are only allowed to answer yes or no. Okay, before starting the game, let's make a little digression. Note that you are equally likely to pick any of the 8 letters because you're just putting a hand in and picking a letter. So probability of picking any letter is therefore the same and equal to 1 over 8. So just for our convenience, let us call P1 the probability of picking A, P2 probability of picking B, etc. And all of these are, of course, equal to 1/8. Why do I do that? Because I want to compute the Shannon entropy. So this was the expression for the Shannon entropy. I substitute the values, and what you get is the value 3. Keep that in the back of your head. And now let's start playing the game. So you've picked a letter, and I ask you, is it in A, B, C, D? Is it one of these letters? So of course you can say yes or no. So if it is yes, then you know that it is one of these 4 letters. So I then ask, is it in AB? It can be yes or no. If it is yes, then I know it's either A or B. So I ask, is it A? If it is yes, then you know for sure that the letter is A, otherwise it's B. And if it was no at this phrase, then it is either C or D. So you ask, is it C? And proceed. Yes or no would tell you whether it's C or D. And here, similarly, you start with this half, and you ask, is it in EF? Or if it's no, you can see it's in GH. So the average number of questions I need to ask in order to guess your letter correctly, you see, is 3. Every time you're asking 1 question, 2 questions, 3 questions. 1, 2, and 3, etc. And this, what did we see in the last slide, is equal to the Shannon entropy. So you see, this gives a nice interpretation of the Shannon entropy as the average number of yes-no questions that you need to ask in a binary search algorithm. This is called a binary search algorithm because you're always dividing your set into 2. So Shannon entropy of a random variable is a measure of its uncertainty. And due to this duality between information gain and uncertainty, it is therefore also a measure of the information gained on average when you learn its value. And there are, of course, many other entropies, Rennie entropy, Salis entropy, etc. So what is special about the Shannon entropy? The answer to the question is, it has an important meaning in classical information theory. It is the answer to Shannon's first question. So this was Shannon's first question. What is the limit to which information can be reliably compressed? Reliably means so that you can later decompress it and get back the information. You want to compress an image, send it to your friend, and the friend can decompress and see the image. And this limit is called the data compression limit. And this data compression limit turns out to be the Shannon entropy of the information source. So to understand what is meant by data compression, let us consider another simple example. So consider 4 horses taking part in frequent races. And the information of interest is which horse wins. So let's label the horses, say A, B, C, and D. And of course, as you know, everything has to be stored in bits in the digital device that you're using. So let's denote A by 0, 0, B by 0, 1, C by 1, 0, and D by 1, 1. So you 0, 1, if you get the message 0, 1, if that's transmitted, then you know that horse B has won. So I've done no compression here. So without compression, 2 bits are needed to specify the winner of each race. But horses have different abilities. So say A is faster than B, who's faster than C, and C and D have similar abilities. So A is the fastest horse and is therefore most likely to win. Now suppose a gambler wants to look at the data of all races in the past 3 years in which the horses have participated before he makes his bet. So the winners of successive races will be something like this. So you see A appears more frequently because A is the fastest horse. So my question is, can one use this extra information about the horse's abilities to now compress the information in the sense of using fewer bits on average to specify the winners of the horses, winners of the race? So let's give them probabilities. Say A has a probability half of winning, B a quarter, and the others 1/8. So now let's do something different. So instead of using 2 bits for storing the labels, let's use just a single bit, 0. Let's say 0 denotes A, 1, 0 denotes B, 1, 1, 0 C, and 1, 1, 1 denotes D. So now, suppose the gambler opens and sees this whole string. He can easily infer who the winners are. Why? Because the first 0 would mean that A has 1. The second 0, again, A is 1. Then 1, 0 means B is 1. Again, A, and then B and C. So you see, no information has been lost. But let's calculate the average number of bits used per race. So you see, you use 1, a single 0, with probability half, 2 with probability a quarter, etc., etc., and you get the value 1.75 bits, as opposed to the 2 bits which we were using before we did compression. And Shannon entropy, if we computed, this was the formula. Let's call this P1, P2, P3, and P4. If you compute that, it comes out to be exactly the same value. So what do we see? That the average number of bits per race is equal to the Shannon entropy and is equal to this value. And what have we gained? We have gained compression, because before we were using 2 bits, and now on average we need just 1.75 bits. And also what's nice is if you use fewer bits on average, then information is irretrievably lost. And here there is no information lost. So that's why the data compression limit can be understood to be the Shannon entropy of the source. It is the limit. If you use fewer bits, you lose information. So there are also entropies of not just one random variable, but say 2 random variables related to the Shannon entropy, something called the conditional entropy. So this is, let X and Y be 2 random variables which are generally correlated. Let me give you an example. So let X correspond to the weather being sunny or rainy. And then the Shannon entropy of X would just mean the uncertainty in the weather. But let's now introduce another random variable Y, which corresponds to the place being either Arizona or Scotland. So then I can introduce a quantity which is just the uncertainty in the weather when you know the place. So obviously this uncertainty is less than that uncertainty. Why? Because if you know the place, your uncertainty about the weather is less. So if you know that Y is Scotland, then it is highly likely that X is rainy. It rains a lot in Scotland. And if Y is Arizona, then it is highly likely that X is sunny. So this quantity Hx given Y is called the conditional entropy. I would like to introduce one last entropy that is also to do with 2 random variables, and it's called the mutual information. I will denote it by I of X and Y. And one can understand it as the amount of information which is common between X and Y. Or in other words, the amount of information you gain about X when you learn Y, or vice versa. So let me explain this through an example, an application that is communicating over a noisy channel. So here is, say, someone called Alice wants to send a message to Bob through this channel, which is noisy. And let the input be X and the output be Y. And as we saw before, the noise distorts the message sent through the channel. And what do people do? Every single day, what do? We use error correcting codes to overcome the effects of this noise. But no matter how clever Alice and Bob are in devising clever error correcting codes, there is a fundamental limit to the amount of information that can be reliably transmitted through the channel. Reliable meaning Bob understanding what Alice was sending. So if no matter what information is sent, the output is completely just some garbage, garbled, then there is no way Bob can figure out what X was. So the capacity of the channel is the quantity which gives this fundamental limit to its message ability to transmit messages through it. So it's the maximum number of bits of message that can be transmitted reliably per use of the channel. And it turns out Shannon proved the theorem that this quantity is given in terms of the mutual information of X and Y. And that's very logical, isn't it? Because if there was nothing common between Y and X, then there's no way Bob can figure out what X was through Y. So it is a measure of the common information. So you see, this answers Shannon's second question about the maximum amount of information that can be transmitted reliably per use of the channel. So this maximum rate is called the capacity of the channel, and as we saw, it's given in terms of the mutual information. So we see that Shannon's answer to his first question, which was dealt with compression of information emitted by an information source, and Shannon's answer to a second question, which dealt with transmission of information through a noisy channel. These are the two pillars on which classical information theory lies. And this theory addresses this question: what are the ultimate fundamental physical limits to communication, storage, and processing of information? And these are both characterized by entropic quantities. Okay, let's now move on to entropies in quantum information theory. So what is quantum information theory? It is born out of classical information theory, which, as we saw, was the mathematical theory of storage, transmission, and processing of information. And quantum information theory 1 asks how these tasks can be accomplished using quantum mechanical systems. So it lies in the intersection of quantum mechanics and information theory. So you know that when you go to subatomic and atomic particles, microscopic level, electrons, photons, and ions, they no longer behave according to the Newton's laws of motion, classical physics. The theory that governs them is quantum mechanics. And quantum mechanics can be counterintuitive and fascinating. And it also has certain features which have no classical counterpart. So in quantum information theory 1 asks, what would happen if we use quantum mechanical systems, for example, photons, electrons, and ions, as information carriers? How well could information processing tasks like data compression, data transmission, etc. be accomplished? So what are the ultimate physical limits to communication, storage, and processing of information when you harness the laws of quantum mechanics? Here are the photos of some of the founding fathers of this field who are still very active: Peter Shor, Charlie Bennett, Alexander Hollego, and Benjamin Schumacher. This is a very incomplete list. And I wanted to mention that the seeds of quantum information theory were already there, sown in the works of people like Stratonovich, Gordon, and Hellstrom way back in the 1960s. So what happens is that the underlying quantum mechanics leads to distinctively new features, and these can be exploited to improve the performance of certain information processing tasks, as well as accomplish tasks which are impossible in the classical realm. Okay, so let's start with the basic unit of quantum information theory, and let me touch upon some of these fascinating features of quantum mechanics. So the basic unit of quantum information theory is called a qubit, coming from the word quantum bit. It is the state of a two-level quantum mechanical system. For example, it could be an electronic spin, the two levels being the upspin or the downspin. Or say the polarization states of a photon, which means say vertically polarized or horizontally polarized, or right circularly polarized and left circularly polarized. So in analogy with classical information theory, as a bit takes a value 0 and 1, we say a qubit takes a value which we denote by this symbol. We call it a ket 0 and a ket 1. So what would this ket 0 mean? Here, for example, it could mean the upspin state of an electron and a downspin state of an electron, or these two polarization states. However, there's a big difference. A bit can only be 0 and 1, or 1. But in quantum mechanics, you have this principle which allows superpositions of 0 and 1. So for example, you could get a superposition of upspin and downspin to, for example, get a spin in this direction. Also, to learn anything about the quantum state, you need to measure it. But as soon as you measure, measurement disturbs the quantum state. So if you measure the spin, it collapses to either an upspin or a downspin. This is another feature of quantum mechanics. Finally, let's talk about entanglement. This is a novel type of correlation that can exist between quantum systems. So these are two quantum systems. They can be very far apart. I just denote this dotted line to say that we're talking about the two systems jointly. They are said to be in an entangled state when it is impossible to describe the state of this orange system independently of the state of this dark blue system, and vice versa. Why do I call it a novel type of correlation? So even if these systems are very far apart. So let me explain the novelty. Let me take an example. So that you have these two qubits, and they are in a state such that you can have complete knowledge of the joint state of the two qubits, but no knowledge whatsoever of the states of the individual systems. Now, this is, of course, impossible in the classical realm. If you know everything about two parts of a system, the whole system, you know everything about its parts. So such a 2 qubits in such a state is said to be in a maximally entangled state. And you measure entanglement in units of, say, ebits, and the amount of entanglement in a maximally entangled state of 2 qubits is said to be 1 ebit. Yeah, we'll come back to it later on. So what happens when you have 2 qubits in such a maximally entangled state? Suppose Bob keeps his qubit and Alice goes all the way to Saturn. So they're very, very far apart. But then say Alice decides to do a measurement along a particular axis of the electronic spin and gets an upspin. Then Bob measures and he gets a downspin. So what seems to happen is there's an observation here in Saturn, which leads to an effect here on Earth, even though they're so far apart. So the spins are anti-correlated. And if Alice gets downspin, then Bob gets upspin. This is if it's prepared in a particular maximally entangled state. So Einstein wasn't happy about this, and he called this spooky action at a distance. But this entanglement is a valuable resource in quantum information theory and allows us to do some tasks much better. So, but let's talk about entropy in quantum information theory. So entropy of the state, I'll just denote the state as a green blob of the quantum system, is its von Neumann entropy. And it was defined by von Neumann way back in 1929, before classical information theory was discovered. But analogous to the Shannon entropy, it also quantifies the uncertainty, but the uncertainty of the state of this quantum mechanical system. So if you know the state exactly, in which case you say the state is pure, because you say you know exactly that's a spin in this direction, then there is no uncertainty and the von Neumann entropy is 0. But a quantum mechanical system can also be in what is called a mixed state, which is a statistical mixture of pure states. So with different probabilities, it's in different pure states. And then more the uncertainty in the state, larger the von Neumann entropy. More mixed it is, larger the von Neumann entropy. It also plays a role in data compression, now in quantum data compression, analogous to the Shannon entropy in classical data compression. So what is a quantum information source? It is, for example, a highly attenuated laser. And the information carriers are the photons. So let this green blob denote the state of the quantum information source. And then S of it is the von Neumann entropy of the source. And what one can prove is that the information emitted by the source per use, every time you use it, can be also compressed into S qubits as opposed to H bits in the classical case. It can be compressed in a manner such that it can be later retrieved, so that we compress reliably. And any attempt to compress it into less than S qubits leads to information loss. So this was proved by Benjamin Schumacher in 1994. So in other words, the von Neumann entropy, like the Shannon entropy, is the minimum rate of data compression, but now quantum data compression. But let's look at another interpretation of the von Neumann entropy, and for which no analogous interpretation exists for the Shannon entropy. Why? Because it is in the context of entanglement. So before saying that, let me take just 2 minutes to convey to you that entanglement is indeed a valuable resource in quantum information theory. Let us see why. So it allows one to do tasks which are impossible in the classical realm. For example, something called quantum teleportation, which we usually read about in science fiction. It's very simple. So what happens is, suppose Alice has this unknown quantum state. So she has some quantum information encoded, for example, say a polarization state of a photon, and she wants to send this to Bob. So the information is encoded in the qubit, as I said, polarization state of a photon, but she doesn't know the state, and she has no means to physically send the qubit to Bob. So for example, she has no fiber optic cable through which she can send that photon. All she has is a mobile phone, and Bob has a mobile phone. So they can only communicate classically. So the question is, can she achieve her goal? Can she send the information encoded in this quantum system without actually physically transmitting it, because there's no way of physically transmitting it. And the answer is yes, she can, provided Alice and Bob initially share an EBIT of entanglement. So remember, an EBIT was a maximally entangled state of 2 qubits. So if, to start with, Alice has 1 qubit and Bob has another qubit, such that their joint state is this maximally entangled state, then she can do that. And at the end, or what she can, so she can do some measurement on her qubits, and then take the phone and say something to Bob, and Bob does something on his qubit. Still, there are 2 qubits on Alice's side, but Bob's qubit get transformed into the state which she wanted to send, which almost sounds magical, right? And this is called quantum teleportation and was found by these authors in 1993. So it tells us that EBITs are precious. It allows us to actually send quantum information without physically transmitting anything. So let us say, look at an interpretation of the von Neumann entropy in the context of entanglement. So say Alice and Bob now have an entangled pure state. It's not a maximally entangled state, it's just a partially entangled state. In fact, let's give them some mobile phones and let's give them many, many, many copies of this this partially entangled state. And what do they want to do? They are allowed to only act on the copies that they have locally and talk to each other by phone. And their name of the game is to extract EBITs from them. Why would they want to do that? Because then they can use EBITs for something like teleportation. So this process is called entanglement distillation, because you're distilling pure maximally entangled states from the partially entangled ones. And what one can find is that the maximum number of EBITs that can be distilled per copy of the initial entangled state turns out to be the von Neumann entropy of the local state. So the von Neumann entropy of the orange blob, which happens to be equal to the von Neumann entropy of the purple blob. Okay, so like in the classical case, you not only have the entropy, you have a conditional entropy and a mutual information. And they all stem from a single parent quantity. And this parent quantity is called the quantum relative entropy. It depends on 2 states, which I denote by these blobs. And choosing these states accordingly will give us these different children. And this was defined by Umegaki in 1967. Not only is it a mathematical parent quantity, it also has a very interesting meaning in something called state discrimination. So suppose you're given a black box and this contains a state, and the state is either a purple state or this orange state. You want to find out which one it is. So what you do is you do a measurement to find which of the 2 states it is. Of course, you can make an error. You can infer it to be the orange state when it is actually the purple one, or vice versa. However, more distinguishable the states, less the chance of an error. So suppose the box contained a red and a black ball, that they are more distinguishable than if it had 2 balls which are close shades of green. So the quantum relative entropy is a measure of how distinguishable the 2 states are. So in other words, the quantum relative entropy of a red and a black blob is greater than that of 2 green blobs, which are less distinguishable. So there is the parent and these are the children. But there are other such families of entropies. There's something called the alpha Pets relative Renyi entropy. That's what RRE stands for, which has its own set of children. And then there's something called the alpha sandwich relative Renyi entropy. And one of the founders of that is Mark Wilde, who's sitting here. And they depend on a parameter alpha. So it's not just a single family. There can be different families for different values of alpha. Okay, so actually there's a zoo of entropies. So here, there are 2 that I defined. This is in 2008, the max relative entropy, the min relative entropy. And this is the relative entropy, quantum relative entropy. Okay, and here is the Pets relative entropy, one of the other parents. So these are the 3 parents I talked about. So then in 2016, with my very interesting Belgian collaborator, Konrad Oudenaardt, what we defined a grandparent entropy. from which all these three parent quantities can be obtained. It depends, and of course they have their own children. So we called it the alpha Z relative rally entropy, coming from A to Z, so as to show how all-encompassing it was. So in the entropy zoo, right at the top of the family tree, that's where the alpha Z relative rally entropy lies. So all these entropies are fascinating, not only in their mathematical properties, but they are essential in information theory because they characterize these optimal rates of information processing tasks that I've talked about. So just before we end the talk, just close your eyes and imagine stepping into outer space with me. And let's encounter a black hole. I mean, from a distance, otherwise you'll be swallowed by it. So a black hole, as you know, is a huge amount of matter packed into a very small area. So NASA science says, think of a star 10 times more massive than the sun, squeezed into a sphere approximately the diameter of New York City. So the result is a gravitational field so strong that nothing, not even light, can escape. So the surface of a black hole is called its event horizon. It is the boundary beyond which nothing can ever escape. So Stephen Hawking proved that the area of the event horizon can never decrease. And this must be reminiscent with what I started my lecture, the second law of thermodynamics, which says the entropy of a closed system can never decrease. So what is the black hole entropy enigma? So John Wheeler, he said, take a hot cup of tea. So we saw any matter in its liquid state has entropy, has multiplicity and therefore entropy. However, black hole was believed to have no entropy. It was defined by Einstein in the general theory of relativity and was considered to be completely defined by certain macroscopic quantities like its angular momentum, its mass, and its charge. So John Wheeler asked, what happens if you take your cup of tea and throw it into the black hole? This is called a thought experiment. So initially, the entropy of the system is the entropy of the cup of tea. But then the tea falls into the black hole. Then the entropy becomes zero because the black hole swallows the cup of tea and you're only left with the black hole, and black holes have no entropy. So he says, does this mean that the second law of thermodynamics is violated because the entropy has decreased? So he asked this question to Jacob Bekenstein, who was his grad student, and then Bekenstein conjectured that the black hole must have an entropy, and the entropy must be proportional to the area of its event horizon. And he said that the increase in entropy of the black hole after absorbing the cup of tea would compensate for the decrease in entropy of the universe because of the disappearance of the cup of tea. And his insight was based on Hawking's area theorem, that the area of a black hole, when any matter goes into it, can never decrease. And later, Hawking derived the formula for the entropy of a black hole. So hopefully, I've given you some flavor of entropy and convinced you that it is ubiquitous, enigmatic, and essential. So thank you for your attention. And thanks to those who joined me on my entropy journey. These are my many collaborators with whom I've written papers on entropy. And particular thanks to Jonathan Oppenheim and David Tong, who taught me about the black hole entropy enigma, and Nicole Junger-Halpern for a very interesting chat about entropies. Thank you.
Questions for Nilanjana? Yes, please.
I am a Boltzmann fan. I want to say that, in fact, if you look at the book by Carlo Ciuccignani written in the 90s, Ludwig Boltzmann, The Man Who Cast in Atoms, you can find the references that, in fact, Boltzmann discussed a lot the question that the time arrow is given by the entropy. In fact, he did a seminar even on that.
Okay.
Where at the beginning he had 1,000 students who wanted to attend, and after a couple of lectures, there were only 2 students, and he had a lot of problems with the president of the university because of that.
Okay. So yeah, and I have not followed the history closely, but I'm not saying that this was Stephen Hawking's original idea.
Yeah, yeah.
I'm sure it came from both.
Yeah.
You were talking about information. Once something occurs, that's where you gain information. Can the opposite happen from an event not occur that would be expected?
So, no, not really, because everything is probabilistic. Yeah? So actually, there is a very small probability that the entropy of a universe can be in the mixing of the gases. There is actually a non-zero probability that the red stays there and the blue stays there. Yeah. So, but it is a very, very small probability. Yeah? So you're saying something which is very highly likely. It can also not happen because the other thing with small probability can happen. It's all about probabilities. But I don't think you can get any information loss if something highly likely doesn't happen. But the contrary is true. Yep.
So I guess during the last few slides, you talked about the entropy of the black hole. And I think you said that the entropy will be proportional to the surface area, right, of the event horizon. So is there a way to understand that in terms of the microstates, for instance?
No, so very, 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 very good question. Because I had a long discussion with David Tong about this. So this is an ongoing research which is going on. So supposedly there are certain, because that is still lacking, the idea of what are the microstates. Can one have a Boltzmann-like interpretation of the entropy of a black hole? So there is this first law of thermodynamics, which says that the work done on the change in heat, dq, is equal to T times ds. And T is Hawking proved that the black hole has a temperature, and that he got a formula which was very similar to that. So the change in energy is equal to T times something. And therefore, it is natural to interpret that as an entropy. But there are certain black holes called extremal black holes, for which there is some theory coming from string theory where they talk about some sort of microstates, but it is really an open problem. And because you see, it's general theory of relativity, which is used to talk about outer space, deals with big things, and quantum mechanics deals with little things. And so here, I asked David, so if entropy does, a black hole does have entropy, that means you're contradicting general theory of relativity, because Einstein's theory says it shouldn't have any entropy. And yes, it does, because what did Stephen Hawking factor in his argument was that quantum field theory, so quantum mechanics and general relativity were used in conjunction. So one still aspires for that theory of everything, which will explain conundrums like this. Yes.
In ordinary experience, we all see the effects of entropy in just our lives. What about a place like the sun, where in the sun, small atoms like helium, or I mean like hydrogen, helium, whatever, are being built up into larger atoms? How do you characterize that? I mean, that doesn't seem, it seems to be like it's
but the sun is not a closed system. Yeah, so human beings are also not, the thing about, I said about entropy increasing arrow of time, and so showed people aging. It should be taken in a very loose sense, because the second law of thermodynamics says for a closed system, entropy always increases. So the sun is not closed, and therefore those creations, I'm not an astrophysicist, but maybe you know the answer, but I don't think it can be directly related to the second law of thermodynamics. But if there are any astrophysicists in the audience, please respond correctly. But I think one has to be careful that it is not a closed system, it's an open system.
I have a question. Oh, is there a question?
Yeah.
Go ahead. Yeah.
So I would like to know your opinion about if the second law of thermodynamics has any connection to constructive theory.
To what?
Constructive theory.
What
Is this
constructive
David
theory is.
Deutsch?
Yes.
Okay,
Oh,
David Deutsch is this constructive.
Yeah,
theory. I don't know about it.
Okay, this is
Maybe-
part, so foundations of
If you don't
quantum
clarify.
mechanics. Sorry, we can have a chat afterwards, yeah.
Thank
Or you can tell us a little.
you. No, I don't know, I wanna.
Okay. Okay, but this brings me to something. So I kept telling you about Arthur Eddington, who coined this phrase, arrow of time. And he said that the second law of thermodynamics is like the supreme law of nature. And he has this famous quotation where he warned young scientists who are trying to find a new theory. He said, well, I'm not quoting it exactly, but if your theory does not satisfy the second law of thermodynamics, then there is no hope. It will collapse and you'll be humiliated. So this is, he used words as strong as that for the second law of thermodynamics.
I do, yeah. So you showed the slide with all the entropies and the entropy zoo. And, even in recent years, there were interesting discoveries with entropies. Do you think that we'll continue to discover more interesting entropies, or I guess the question is the zoo tamed and
No.
settled?
No, the two, yeah, but the fact is, I'm in the maths department, okay? So mathematically, people one can construct another entropy. He tried constructing one today, this morning, okay? But the point is, you can keep, it's like entanglement measures. There's a zoo of entanglement measures as well. So you can keep constructing new entropies and new relative entropies. But to me, it's only meaningful if it is of some operational meaning, if it has a meaning. It's not just a mathematical construct, but it has, for example, that relative entropy, you can show that it is a meaning in state discrimination, or some sort of a task, not just some sort of physical relevance. So I think people will keep constructing relative entropies. You will too, I will try to, but we will also keep looking for a meaning for it. So I don't think the zoo is complete at all. So you might need a $3 billion cage like your Mike the Tiger.
Peter, go ahead.
Yeah, so regarding this large zoo of entities, why do you need so many?
Yeah, okay.
Let me go back to the slide.
Okay,
Nice.
so Mark wanted me to talk about something which I didn't talk about. And so it will be very nice that you asked that question. I can explain a little bit. So this was the entropy zoo. So you see, I, of course, didn't tell you things precisely, right? I talked about, I gave you a very simple explanation of things. So when I said, consider, for example, data compression, and I said that the von Neumann entropy is the optimal rate of data compression. Actually, when you want to prove that mathematically, people make a huge assumption. They assume, even for the Shannon entropy case, you assume that you have a source which you can use infinitely many times. And every time you use the source, it behaves in exactly the same way. So this is called, there is no, or you send message down the channel. When you send message down the channel, every time you use it, the channel acts in the same way. There is no memory with this previous action. And you can use it infinitely many times. So this is called the asymptotic memoryless setting. And all these original entropies that we talked about today are obtained in this very artificial setting. Because when you go into a lab or you want to send messages, you don't have infinite number of users of a source or a channel, right? But that was done for mathematical convenience. So a group at ETH, led by Renata Renner and my students, collaborators, and I did was said, okay, let's lift these mathematical but unrealistic assumptions and say you have, say, a channel and you're allowed to use it once, only once, or say 10 times, but not infinite number of times. And you say also, let there be, allow possible correlations. Let there be, the memory effects are also allowed. These are realistic assumptions. So that led to quite recently, 2013, it was probably around that time, to the start of the subfield of quantum information theory, which we called one-shot information theory, or which led to this conference he mentioned, beyond IID. IID means independent and identically distributed. So like we had the Shannon entropy and the conditional entropy, mutual information in this asymptotic IIT setting, what one finds that in that one short entropy case, there is a completely different family of entropies which come up. And those are, for example, the ones that I showed there, the max entropy that I defined, and and this max entropy, and the min entropy, and many of these other quantities. And now if you start with those, and then say, all right, put back those assumptions of having infinitely many and no interactions, you get back the original entropies. So you see these other entropies also have important operational meaning. So thanks for the question. Yes.
Well,
So the pure quantum state has zero entropy.
Yeah, because pure means you know it exactly.
So is there any prevalent kind of universe is mixed state?
You can prepare in a lab.
Universe.
The
is the
universe.
universe in a pure state or a mixed state?
Uh,
Please tell us.
So entropy increase means universe must be mixed.
It must be mixed. Yeah, there are stars exploding. We are there, growing old, doing crazy things. So I think it's not a pure state.
But
Yeah.
initially it could be the
At the back, so you're going back to Big Bang, right?
right.
Yeah. Unfortunately, I don't know what is known about any astrophysicists here. Did it start with a? Well, it was a macroscopic system. Yes, I mean, you have the
I
answer.
don't know if I understood the question, because I'm a mathematician, so I have read in a lot of things you are saying. But I can cite again Boltzmann, because Boltzmann, and I don't know whether it answers a little bit, but Boltzmann were saying that entropy is increasing in the universe, but we have to think here, really, I have the citation, that there exists more than one universe. This is also very often said by Hawkins, but said, well, I have the citation of Boltzmann. And due to the other universe, they can push our universe to shrink again.
Oh wow. Okay.
So in this sense, entropy can again
Decrease, you mean, or
go the other direction
okay.
because of the other
Okay.
universe, because
So-
it's not isolated.
Okay, my universe here was the universe of all the universes, and then it's a closed system.
And then it's a citation of Boltzmann.
Yeah.
But I don't know whether this answers.
It's turtles all the way down.
Sorry?
It's turtles all the way down.
Yeah. Surya, you had a question?
Yeah, you proposed the grand parent entropy, the alpha Z relative entropy. Was that an operational task?
No, that was not an operational task, but that was. So you see all these, why are these relative entropies good? Because we had lots and lots of papers which work out the mathematical properties of all these individual entropies. But if you have the relative entropy, which is the parent quantity, you can just study that. And from that one quantity, you can derive the properties of all its children quantity. So the good thing about this alpha Z relative Renyi entropy was it depended on these two parameters, but by studying it, we could get all the children quantities. And since you asked, let me just finish with a little story. So I grew up in a small town in the state of Bengal in India. It was a really small town, but in that small town, there was one man who'd come from far away. He came from Armenia. So he had a big long name. The first letter started with A and the last letter was Z. And the children loved him, and so we called him Uncle A to Z. So when I wrote this paper, at the end of the paper, you normally put acknowledgements, and you acknowledge the grants which fund you, etc., etc. So if you see the original version of the paper, there's an acknowledgement to Uncle A to Z, because he inspired the name of this.
How do we know that the universe is a closed system?
Because there's nothing outside it with which it can interact. The closed system, in my closed, I meant closed in the sense of isolated. So that means you have to consider the boundary of the universe if you can. There's nothing beyond it. So if there's no exchange of matter or anything, at least I can't conceive of anything beyond the universe. So that's why it's closed.
So in a sense, we've defined it.
Yeah. I think the astrophysicists of Cambridge would be squirming at my responses, but they're probably
Question.
So I wanted to get back to, we were having a conversation about the way you would define, for example, the Alsacian, right? So in general, maybe this is a general question, but I'll try to ask it anyway. So when you're thinking of defining entropies that are higher on the family, and you don't have an immediate operational interpretation of it, I guess what would be the motivation there, or what would be the incentive there to find a specific form rather than?
Yeah, so there it was very, very clear what the motivation was, because we had these three different entropies: the sandwich, the pets, and the normal relative entropy. So, well, I'm becoming more and more of a mathematician, which was mathematical curiosity. Could there be one single quantity, one single parent from which everything comes? And these relative entropies, as you working on quantum information surely know, there's a fundamental quantity, property they have to satisfy, which is called the data processing inequality. That just means when it depends on two states, and if these two states are subjected to the same noise, then the resulting relative entropy has to be smaller than the original relative entropy, because distinguishability can only become worse under the action of noise. And so proving the data processing inequality for a mathematical quantity like that is a wonderful challenge. And that was one of the motivations too.
All right, thank you. Oh, all right.
For one of the slides, you had two cups that qualifies.
Sorry, I couldn't hear you. Can you take your back step?
For the two slides, you had two cups, one with water and one with
Yeah, the ice chips and water, yeah.
It seems like there's a correlation between entropy and the state of matter. Is that correct?
Yeah, indeed, of course, because entropy is directly related to multiplicity, and multiplicity is more in liquid state than in solid state. So the answer is completely right. So in that case, then whenever the multiplicity is more, then entropy will be more.
And also, with the entropy of, let's say, what about the water vapor? How would that compare?
Yeah, much more. Yeah, if you have a gas, there are many more, like the hydrogen balloon I talked about. Yeah? There are many more configurations of the molecules of gas than if you have a water balloon or a hydrogen balloon. The hydrogen balloon would have a higher entropy than the water.
All right, thank you for all the questions. Let's thank our speaker again.
I'd like to thank somebody. Zach. Thank you very much for all your help in the logistics of the travel and making this trip possible.